Okay, hello everyone. So, a couple of things for today. The first thing is I wanted to make a comment on using power on demand. Don't, at this point, I'm going to say don't be shy about using it. If you have any use for it at all to do anything, use it. Uh, Let me show you why, at the risk of having people go overboard. Um, this is what our current usage looks like. I was originally a little bit concerned. We're fine. Don't worry about it. As long as you don't have like 5 of them open at once and running around the clock, it shouldn't be an issue at this point. Use however much power and demand time you think you need. Uh, the second thing is I would like to go through a little bit about how we can visualize things in some slightly fancier ways and how we can measure things in some slightly fancier ways. Because you know at this point enough, I think, where you could simulate the basic flow around a lot of different geometries, as long as you could get them in, as long as you could import them into Star in the form of a parasolid file. You could probably mesh them, and or well, at least theoretically, capability-wise, you might not have the computing power to do so. You could probably mesh them, probably run them, probably understand if it looks like they've converged reasonably or not. Um, and you can already look at basic pressure fields, velocity fields, etc., using planar sections or surfaces. But I wanted to look a little bit more in depth at a couple of fancier things. I mentioned some of them before, but I want to go more in depth with them because they're very useful for visualizing some types of phenomena. So, first of all, let me just go through the setup that we have here. We have a wing in a wind tunnel. This one is not half of a wing, it is the entire wing. So, let me just step through the domain that we have here. We have a rectangular domain of air. You can if you look really closely, you can see a wing hiding in the middle here. This is our air domain. We have a couple of regions that are refining the mesh around this wing. This isn't the wing itself, obviously. This would be a very poor wing if it were. This is just a region with a couple of other regions nearby to refine the mesh in particular areas around this wing. This is the wing itself. Notice a couple of things. It has a fairly limited aspect ratio for starters here. I forget exactly what the chord of this is. Let's see if we can figure out what the chord is. Measure. Why isn't this letting me measure? There we go. So it's got a 1 meter chord, and it also has. Okay. It has about a 6 meter span, so this is a pretty low aspect ratio wing. It also has some dihedral to it. Notice how the wingtips are swept up. It has a narrow, flat section in the middle, and the rest of it has a couple of degrees of dihedral built into it. As well as the wingtips, instead of just being flat, planar sections, are actually rounded. This is actually a solid piece. I'm not showing it for some geometry scene. Parts. We can get rid of everything, so I only want to show you wing itself at this point. Parts, wing, surfaces. Well, that's curious. Why isn't it showing me anything at all? Oh, latest surface geometry. There we go. That's better. So this is the wing itself. We can see that the wingtips are rounded. There aren't any particularly sharp edges anywhere. There's maybe a couple of tiny geometric artifacts on the edge here. This is the sort of thing you might actually want to keep an eye out for. In this case, it's small enough that it probably doesn't matter, but it can. Small things like that can produce anomalies if you're not careful. But this is the geometry we're working with. Again, we have it in a rectangular domain. We have, let me scroll down here. We have the usual. Sorry. Hard to see. Everything except for the front is a pressure outlet. We have an inlet. Sorry, the sides are pressure outlets. The front is a velocity inlet. And specifically, we are driving this at 15 meters per second, so give or take 100 miles an hour. The back is a pressure outlet, and the wing itself is, of course, a wall. You can tell from these symbols, or you can read it off on the type here under properties for the various faces under regions. Let me go through the mesh really quickly here. I don't think it actually needs updating. It's just complaining about that. So, of course, we have it. So we made the far field, the surfaces, the free air surfaces far away from the wing. We made them a lot coarser. You can see I cranked up the minimum and the target size a lot for those. We have several volumetric refinements. We have one for this trailing edge of the airfoil, because trailing edges are difficult to mesh often. And this is just turning the size way the hell down, as well as limiting the prism layer thickness back there. Let's see if we can look at what the mesh looks like. So if we look near the trailing edge, it's actually a pretty crappy mesh. I do need to remesh this. Oh yeah, I don't think this was enabled for that. Okay. I don't know how long this will take to remesh. Let me check how many cells are in here. This is an older simulation I threw together for rough demonstration purposes. Okay, I'm not going to try and remesh this just yet. This should probably be rerun. But we're not going to do that just yet. As a matter of fact, this probably needs to be like 3.125. And layer thickness of like... probably fine for prism layer thickness. Last but not least, we have a couple of volumetric refines near the wing tips that are not refining the trimmer mesh. So this does nothing. This one does nothing for the volume. This only acts on the surfaces. This is only modifying the surface remesher. It's not modifying the prism layers. It's not modifying the trimmer. However, it is making the wingtip surfaces meshed finer. So out here on the surface. Then the same parts, these conical shapes, are used for volumetric controls, where they don't modify, or they do modify the surface mesher. They also modify the prism and the trimmer, and they bring it down to 50% of base size, with a limited prism layer thickness as well. Notice the prism layer thickness drops right where the edge of this is, because it was told to go from whatever it was before to 50% of the base size. And you can see the size on the surface of the wing also gets smaller as it moves over. And then last but not least, this entire region was constrained to be no larger than 100% of the base size. You can see that hemispherical front and the rectangular body superimposed in it. So I probably would need to rerun this, but we'll go through with the visualization process anyways for the moment here. And then we'll circle back around and maybe remesh that towards the end here, depending on how long this takes. So this is the setup here. Again, the trailing edge isn't the greatest thing in the world, but it's sufficient to show us how to visualize something. And those are a couple of different things. The big one that I'm going to go through is streamlines, because those are very useful to know where the flow is going. I actually already have one made, but we're going to go through making one again and going through how you make them. So streamlines are derived parts. They don't exist as a physical fundamental, or they don't exist as a physical definition in three-dimensional space inherently. They only exist because of the properties you give them. And how they look depend on the properties of the flow field. So if we go to derived parts, new part, we have a whole bunch of options. Streamline is one of them. We also have constrained streamline, which is a little bit of a special case. So we're going to go with streamline. So when you make a streamline, you have, if you have a geometry or a graphics scene open, you'll get this sort of display that lets you see where you're putting them in three-dimensional space. We'll get to this in a second here. So what do you have? Input parts. This is the region in which the streamlines will exist. In this case, we only have one region, so we select it. If you had multiple regions, the streamlines would only exist in whichever region was selected here. If you had, for example, this domain cut into two pieces, front and rear, and you only selected the front, the streamlines might come through here and then stop. They would not proceed into the region that was not selected. It would only exist in whatever region is selected under input parts. Second is seed mode. How do you generate the streamlines? Well, let's recall for a second, what is a streamline? In transient cases, it gets a little bit more complicated. But for the sake of argument, for a steady state case, it is the path that the flow takes. Right? If you drop a particle into the flow and follow it, that will trace out a streamline in steady state. So effectively, the seed mode is, where do you drop that particle into the flow? Now, you can do this in a couple different ways. You can put those points on a surface, which is what it means by part seed. So for example, we could say it's in part seed mode. So it wants us to select a part, a boundary to seed these streamlines on. So we can select our inlet. And then it has resolution. So this is how many streamlines in the X direction and how many streamlines in the Y direction does it place. This is a little bit fuzzy because your surfaces aren't always going to be nice and rectangular. This is kind of an approximation for the array size of streamlines you want to play. It's not necessarily going to be the exact number, but it'll get you pretty close to the number of streamlines it creates. So let's just take a look. And also you can pick what vector field you want it to plot. It has to be a vector field for starters. However, it can be any one of these vector fields. Usually this is velocity, because that's how we treat streamlines. But technically, you can create a streamline, quote unquote, for any vector field. So if you create a streamline for vorticity or area or lamb vector, normal position, or anything other than velocity, really, it won't technically be a streamline because it's not following the path of velocity anymore, or it's not following the path of the flow anymore. It's only really a streamline if you select velocity, but you can create a streamline part for any of these. The math works out the exact same as long as it's a vector field quantity. We will leave it selected as velocity because that's kind of the useful one. I'm going to click OK. Click OK. Why isn't it taking this? Oh, because I haven't changed anything. I didn't actually change it away from what it already had selected, so it didn't let me click OK to change something. And then last but not least, you have direction. So I said see this on the inlet. So let's just go ahead and look at this really quickly here. We're going to not create a displayer. I'm going to go create a new scene really quickly so we can look at these. So let me go ahead and click Create. And we'll see that under Derived Parts, Streamline 2 showed up. Hey look, we have a 5x5 array of lines passing through our domain. A little bit hard to see them. Let's go ahead and create a new scene. I'm going to start with an empty scene to visualize these. So this scene is currently empty. It has no displayers. I'm going to create a new displayer so we can look at the surface of our wing. So I'm going to go in here, go to Geometry, Parts, select our wing. And I don't care about this changing with the mesh, so this is just going to be the geometry representation of our wing, because this doesn't really have a mesh on it. Okay, now let's go create another new displayer for a streamline, which has its own displayer type. We will go ahead and under Parts of our streamline displayer, we are going to select Streamline 2, the one we just made. We can see a whole bunch of lines. We can see most of them just run straight through the domain, except for this one in the middle. Right? This one in the middle hits the top of the wing and follows it around, and actually goes down behind the wing. This is what we'd expect. It's also not actually plotting this. These are following the path of the flow. These are streamlines. But just because they're streamlines doesn't mean you have to plot velocity on them. You can plot whatever you want along the path that this streamline is following. Let's go ahead and plot pressure coefficient for a second here. We can see that most of this is all the same until it gets to the top surface of the airfoil where the pressure coefficient drops dramatically. Now this isn't terribly accurate, and I'll explain why in a minute here. Actually, I'll explain why now. It's because this is plotting pressure coefficient. Well, if you are familiar with how pressure coefficient is defined, it's defined with respect to your free stream dynamic pressure, and it's defined with respect to your free stream static pressure. Well, guess what? How does the software know what your free stream dynamic pressure is? You could have multiple boundary conditions. You could have multiple different inlet velocities depending on how complex things are. It really doesn't know. In order to tell it what reference values to use for various coefficients, you have to go down here into Tools, into Field Functions, and we're going to go down to Pressure Coefficient. Oh, hey, look. This thing's density is 1. It's really not. It's going to be pretty close to 1.18. It thinks reference pressure is 0. That's all well and good. But it thinks our reference velocity was 1 meter per second. Nope, not right. It's 50 meters per second. So we're going to change this to 50. And we see that our pressure coefficient goes to a much more reasonable value of a little bit above -1 on the upper surface of the airfoil. Much more reasonable. If you ever plot coefficients graphically in STAR, make sure the reference values are correct. If you do not, It will use something silly like 1 meter per second when your free stream velocity is far faster. And it will give you bogus results. But anyways, so you can plot any value on these streamlines that you want. You can plot velocity magnitude, you could plot pressure, temperature, density, Mach number, whatever. Doesn't matter. You can plot whatever you want on these streamlines. The streamlines themselves are based on velocity, but you can plot whatever scalar field you want on them. Now, this, again, is an example of a part seed. We seeded this on the inlet. Now, let me go back to where we defined that for a second here. We have a couple different ways to do this, though. We can tell it to propagate in the forward direction, where it's following the flow in the positive velocity direction. We could also tell it to propagate backwards, at which point the streamline starts and immediately goes backwards out of the domain and doesn't show us anything. Or we could tell it to go in both directions, forward and back, where it shows us the forward direction again, and the back direction proceeds backwards out of the domain. This will make more sense in a second once we look at the other mode that we have, because, again, part seed is starting our streamlines on the surface of a part. It doesn't have to be the boundary of a surface necessarily. We could also tell it to do something like, let's see here. You remember that refinement region around our wing? We can start our streamlines on that. Apply. Close. Oh, did it not actually update? I don't know if it updated. Edit part. There we go, I think. Ah, yes. Okay, yes. It is actually seeding it on that part now. It's just doing it in a rather peculiar way. It's also only showing us one of these, which is interesting. Tell you what, I'm going to try something really quickly here. Let's take a look at this wing refine. Let me just split it up a little bit. So we have the leading edge surface. This might demonstrate a little bit better what's going on here. So let's try and seed this on that surface. Wow, it really does not want to work for me, does it? It is absolutely seeding it on that, but like I said, when it seeds on surfaces, especially curved surfaces, it can act weird. Try this one more time. If this doesn't work, I'm just going to move on, though. Yeah, it really doesn't seem to like me for some reason. Okay, well, we'll go on to the second mode. surface isn't necessarily the only way to do this. We could also define points in space. So, for example, let's define a point that's going to be about 0.5 meters upstream of the wing and 0, 0. So negative 5, 0, 0. 0.5 meters upstream of the wing in the middle. Actually, no. We're going to put it about halfway down the left side of the wing. We're going to put it negative 3 meters in Y. We'll put it a little bit up, 0.05 meters. So it should be in front of the wing over here and slightly above the 0 or the origin here. And you can define at this point how big of a radius you want to do. Now let's do 10 centimeters, and we're going to put 15 streamlines. And we can check this little box to have it show us where this is. So it's putting a point a little bit below the wingtip, very near the wingtip. Let's do negative 3.1 and move this up to 0.2. There we go. So now this point is basically immediately in front of the wingtip. And it's going to put inside a 0.1 meter radius, let's actually make this 0.2. It's going to put inside a 0.2 meter radius of this point 15 streamlines. It's going to drop 15 streamlines effectively at random inside of a sphere located at that point with that radius. And it's going to propagate these forward in the velocity direction. Fly. Ah, look at that. Now these are a little bit clustered. It's really hard to see what's going on, but you can see there's a vortex there. Exactly like we would expect for a finite wing. So let's talk a little bit about how we can modify the appearance of Streamline. We added a Streamline displayer to our scene. We were plotting pressure coefficient. That's all well and good. Although I'm actually going to change this to plot velocity magnitude. Keep things a little bit slightly more consistent. But it's really hard to see actually what path they're following here, right? Really hard to see. So how do we change that? Well, you can change as a property of the Streamline displayer, not the scene. The scene is here. As a property of the displayer, we can change what they look like and what they're plotting and how. So you can make them slightly transparent if you wanted to. You can change their opacity. One thing you can do. I'm going to leave this at 1. You can make them either infinitely thin lines. No matter how much you zoom, they're infinitely thin. They're lines. They're single pixel lines. This can be kind of hard to see though, because they're single pixel lines. You can also make them ribbons, which makes them lines extruded left and right, and then they rotate, and you can see, oh boy, do they rotate a lot in the middle there. And you can make these ribbons wider or narrower. And like I said, you can see that those in the middle are kind of going absolutely bonkers with how much they're rotating. How they're oriented can change a little bit. Like I said, some of these are rotating a little bit, some of these are rotating a lot. Personal preference is stream tubes, although stream ribbons can be useful to show things like this, where you have extreme amounts of rotation in the flow. And then you want to tweak the thickness of them until it's reasonably easy to determine what paths they're following and generally what's going on with them. You don't want them so small that they're effectively lines again. That doesn't tell you very much. You don't want them so big that they're just one giant cluster and you can't tell what's going on. You want them somewhere in the middle, where you can identify discrete paths, but also they're large enough where you can easily see them. And then you also have some other settings you can mess with down here. It doesn't really matter too much. I don't think I normally wind up using any of these. But as before, we can either have these propagate downstream, upstream, or both. So right now they're propagating forward. Let's have them propagate backwards. They still have a little bit of rotation because they're starting to get close to that leading edge of the wing, but they're mostly just going backwards out to the inlet. And we can control also how far do they propagate. Let's only ask them to propagate 2 meters. Well, they go 2 meters and then they stop. Also, the math, you can control how many integration steps. If you go to an extremely low or large number, it's only going to integrate twice. And it only gets that far. The default values for integration steps is usually okay. The maximum propagation can vary depending on how big your thing is. You can change the initial integration step to make things a little bit more accurate. Notice with 0.5, it changes how much they rotate just a little bit. One thing to note, if you create too many streamlines, they can take a long time to compute. Be careful. Don't go crazy and make like 1,000 streamlines. It'll be impossible to see, it'll take a while to calculate, and it won't be particularly useful. I'm going to have these propagate both backwards and forwards. And up to 20,000 steps. Now, compared to an initial integration step of 0.5, definitely they are still following the same path pretty closely, but the rotation magnitudes are a little bit different. Not by much, but a bit. Again, you have an option of Streamlines, which has no rotation to it. It's just a path and a value. Stream Ribbon, which is a path, an orientation, and a value. And then Stream Tubes, which are a finite thickness line following a path. Most applications, I prefer Stream Tubes, but it can vary which one is preferable depending on what you're doing. So that's a stream line, or the various implementations thereof. Oh, wait, one more thing. That was a point seed. We can also do, instead of a point seed, we can do a line seed, where you put, instead of them randomly in a cluster, you put them in a line from one point to another. So let's put this at negative 0.5. So we're going to try and create a vertical line. Instead of a random cluster, we're going to try and create a vertical line, more or less where we already put our cluster of points. So we're going to start at ½ meter in front of the wing. We're going to start it at 0.5 meters, and it's going to descend to negative 0.5 meters. See, these spheres represent the center points. It's just not. There we go. If you click on it, it'll resize them a little bit more appropriately. So, and we want to put them out near the wing tip. Maybe not quite that far. So negative 3.1, I think. That's pretty good. And we can put, let's say, 40. Well, we have 40 streamlines. It's seated along a line vertically. If we only want them to propagate forward, we can change the integrator again to only go forward. We'll see it start right about here. And they proceed downstream past the wing, and we can see the very nice formation of a wingtip vortex off of this wingtip and this wing. It's not a huge, colossal amount of rotation just yet, because it's actually slightly outboard of the wing. Let's go ahead and take this line seat and tuck it in just a hair. Let's see here. Oh, it's recalculating already. See, it's taking a second to calculate 40 meters per second, so, or 40 streamlines. We can tuck it in a little bit, and we get a little bit more pronounced rotation. We can tuck it in a little bit more here. Let's go 0.5. And we're going to get slightly more pronounced rotation. You can see it splitting just a hair over that leading edge. So line seat is the other way. It gives you a little bit more control, a little bit more control over exactly where the streamlines are put, and makes them distributed more randomly, more uniformly over the space that you've indicated. We also have a constrained streamline, which is a little bit more complicated in some ways. So let's go ahead and do the same thing and plot. We want it to plot this on the air region. We want to do a, let's say here, a point seed. So same thing in front of the airfoil. We'll do it at the other wingtip. So this is going to be like 3.05 and 0.2. Seed radius 0.1 and 15 of them. Vector field will be the velocity field, and we'll only propagate forward. And we're going to add it to our existing streamline displayer. Let's see what this did. Well, this doesn't look like it did much of anything, now does it? Well, as an interesting thing, note that it doesn't really let us select anything other than surfaces. It doesn't let us select a volume. Notice how there's not a big square here. That means this isn't a volume we're selecting. That means these are surfaces we're selecting. So let's mess around with this and see if we can get this to show up a little bit, shall we? So we're going to put this on the middle of the wing instead. Hold on a second here. Okay, so I believe what this is related to is the fact that with a streamline, we have or with a constrained streamline, it has to be seated, or it really should be seated on the surface, and it only ever takes it only ever takes points, or it only ever shows streamlines on surfaces. So let's go ahead and make this a part seed. We're going to go ahead and select the walls and the inlet. See if we can get anything to show up. I don't think it will. Constrained streamlines appear to be a bit weird. Nope. Okay, just stick to regular streamlines. Honestly, I hadn't used constrained streamlines because they hadn't been needed, because they do weird things, apparently. Regular old streamlines, though, very useful. This is a very, very useful indication of exactly what the flow around this trailing edge airflow is doing. Something that no planar section could ever capture very well. Last but not least, let's see if we can use this to show us where the vortex core is of this wing. Oh, it's calculating. Aha! Notice how it's attempting to locate where the vortex is on the surface of this wing and plotting it out. Let's see here. Strength. 0 minimum length. Let's do 50. And it's very difficult to see in here, but it's attempting to plot where that vortex core is. You can see this thin black thread winding its way through the there we go. You can see the now stream tube winding its way kind of from the wingtip downstream of the wing. You can mess around with the parameters a little bit to try and show where the vortex core is a little bit more exactly than that. Or you can just use streamlines to show that, hey, yeah, there's a vortex there, all right. But streamlines are the big one for this. Now, this is the other way to visualize flow, or one of the other big ways. We can also make a cylindrical section. So instead of making a planar section through the flow, we can start at, let's say, negative 0.5, oriented in the x direction. This will be negative 3.05 and positive 0.2. And this will have a radius of, let's see, 1/4 meter. And you can create a cylindrical section. Now, this definitely looks rather lumpy for some reason. Not entirely sure why. I think it's only taking cells that are entirely enclosed, and this is the cells that are entirely enclosed because the cells get pretty big as we go further away from this wing. Oh no, it's taking cell boundaries is the thing. That's what's going on. Let's crank up the radius just a hair, or just a lot, actually. There we go. Well, they look more reasonable. You can see where the cells go from relatively large to relatively small as they get closer to the wing. And we're plotting the surface of that as a cylindrical section, or the attempt at a cylindrical section. And then we can open up a scalar scene, new scalar scene, and we can plot on the surface of this section that we just made. Where did I put it? We just made a cylindrical section, not planar in nature. We can plot whatever quantity we want. So let's just plot pressure coefficient again. We can also see how granular the cells are. As they go from small to large, we can see where the airfoil intersects around this approximately cylindrical section. It's actually pretty damn close to cylindrical, really close to the airfoil. It's just as the cells get bigger, further away, downstream and upstream, the approximation of cylindrical becomes much looser. Sections do not only have to be planar. There are multiple types of sections you can make, including a constrained plane. Well, what is a constrained plane? It is absolutely just like a regular planar section, except you can limit how big it is. So, like, normally if you made this planar section, this entire thing would be filled up with a plane, right? What this lets you do is you can modify where the plane is, but you can also put a contour on it. And say, hey, I only want to plot everything that is inside of this curve. Boom. It's plotting pressure on all cells that fall inside of that curve that I just made. This is a constrained planar section. Last but not least, very similar to the way that we did points that we did points and lines for streamlines, we can create sensors. You can think of this as pointing at a particular location in the flow and saying, I want to know about something here. So let's just create a couple of points here. We're going to just drag this to a semi-random point. Kind of vaguely near our airfoil. There we go. So assuming this is actually in the flow, we can go ahead and create a sensor at that point. Now, if we click on this point, we can see that it highlights where it is in three-dimensional space. And we can ask for any of a report. Let's just say, let's look at what's a good value? Flow energy, not really. Oh, right. We're doing a point. So really we need to do maximum or minimum. So if we're looking at a point, when you take the maximum, it's the same as the minimum because it's the value at a single point. Let's look at pressure. And we're going to look at this specifically on our point probe. Oh, wait, sorry. I'm double-clicking on the point, not the maximum. There we go. So pressure at this point is 431.9 blah, blah, blah pascals gauge. You can also create a section or a line of probes. So let's go negative 0.5. Let's do 0, do 0.5, negative 0.5, also 0, negative 0.5. So we're going to create a line of probes that are in front of this airfoil. No displayer. We're going to create 20 of them. Create. So if we look at this line probe, we have a collection of them. And we can look at other things for this as well. Let's see here. We can look at the maximum, minimum. We could look at line integral. We could look at other things. So let's do the same. Well, actually, let's just add this to our maximum, minimum. Let's look at, actually, let's make a new minimum. New user minimum pressure. And we're going to select both things that we just made. We're going to select our line probe and our point probe. And we're going to run this. Oh, I did not tell it. Oh, I put pressure in the co-located field function, not the actual function. There we go. Ah, there we go. So it's still 431.9 on the point, but the line has a minimum of -69. Okay. Well, let's also do a grid where you can plot an arbitrary XY array over whatever point, whatever plane you so choose. And you can limit the size of this, or you can reorient it in three-dimensional space. Changing the size of it, etc. So let's just do that and create. Let's see here. We have a grid of points. A little bit cut off because it clips out of the top, bottom, sides, whatever. But this is a grid of points that we can measure stuff on. Let's go back to our minimum. And I need to wrap this up in just a second here. But let's go back to our minimum and pull up our presentation grid. And run our report again. Well, these are the same. But now we also have a value, a minimum value on this entire grid. I believe what we could also do is let's pull up that scalar field. And let's just plug in all of these. We can also plot points or pressure at points. Go ahead and hide this. Hide this. And we can see what, or pressure coefficient as it were. And we can plot pressure on these points, on this grid, on this array, what have you. And really quickly, I think arbitrary will let us do potentially some interesting things by plotting on part surfaces. So if we take the surface of our wing, we get a whole bunch of points along the edges of our wing. So arbitrary is a little bit harder to constrain, or you could give it a series of XY points in a file. But you can also do an arbitrary plane or arbitrary probe selection, which does some other interesting things. We're going to go ahead and leave it there, but these are some ways you can show other quantities, and probably should show other flow quantities, other flow field effects, vorticity, etc., for highly three-dimensional flows.